Okay, so last week I explained the compressed suffix arrays. Okay, CSATV. GV. Okay. So for a string of length n on a size sigma alphabet, its suffix array can be represented in n times 2 plus log sigma bits plus order n log n over h plus order n log n over log n bits. And an element of the suffix array can be computed in order h time, where h is any positive constant. So, for example, if h is set to be log n, then this term becomes order n. So then the original suffix array uses order, no, not order, exactly n log n bits, but this can be compressed into n times 2 plus log sigma bits. Okay. Then, so this is a very good data structure for compressing suffix arrays, but there are some drawbacks. One is if we do pattern search, we also need the string itself, because this data structure is just to compress the suffix array, and the pattern search algorithm using suffix array also need the string itself. Okay? And the string uses another n log sigma bits. Okay? So the space is doubled. Okay? And another drawback is that counting query takes order pattern length plus h times log n time. Okay? So here h equals to log n. So there are log square n term. Okay? Then this is slower than using the original suffix array. So we want to handle these problems. So for the first one, we consider self-indexes. So what is it? Given some data t, we consider to construct a data structure d of t to support some operations on t efficiently. So for pattern search on a string, t is the string, and d of t is, for example, the suffix array. Okay, and a data structure d of t is called self-index if it does not require t to support the operations. Okay, so in some sense, the data structure d of t contains the data t. Okay? So if the original data t is required to support some queries, then the working space cannot be smaller than the size of t, of course, because we have to store t. Whereas the size of self-indexes can be smaller than t. Okay? So if we have some algorithm to support the queries, which does not require t itself. Okay, so let's consider self-index for suffix arrays. So first recall that how to do pattern search with suffix arrays. So we have suffix array and the text itself. Okay, then we do a binary search on the suffix array. Okay, so for example, if we want to find b equals ABA, so find the middle entry j, maybe this one. The middle entry is in this case 5. Okay, So j equals to 5. And if we use the complex suffix array, then it takes order h time to find this middle entry. Then we look at the string t and obtain the substring. This one in this case. S equals to be ac data. Okay. Then compare this substring with p. Okay. Then we narrow the range of the suffix array and repeat this until we find the pattern. Okay. So if we use this algorithm, then we need t. And so this means that the suffix array is not a self-index. So we know that the suffix array can be compressed. Then this takes pattern length plus h time, where h is the time to compute one entry of the suffix array. Okay. And for comparing p with suffix, it takes order p time. So the time compressed is pattern length plus h. And we repeat this log n times for binary search. Okay. So if so we need t. But if we can obtain s, the substring, without computing j, then the algorithm may run faster and we may obtain a self-index. Okay. So we want to change the search algorithm. Okay. So first consider obtaining a substring. Okay. So given I and L, I is the lexicographic order of a suffix, and L is the pattern length. Then this algorithm computes the substring, this substring, in order L time pattern length. Okay. So this string is a substring of T, and its position is SA of I. So if I goes to 3, then it is this substring. If L goes to 3. Okay. So how to find this substring S? So this is our algorithm. So this is for loop, and the first character is obtained by psi prime I divided by n plus 1. Okay. So psi prime is computed from the psi function, and the definition is that psi prime I in T of SAI times n plus 1 plus Georgia's psi function. Okay. So from psi prime, we can obtain the first character of the suffix at position SAI, or with lexicographic order I. Okay. So to compute this character, we don't need to compute SAI. We can directly compute from psi prime I. And psi prime I can be computed in constant time. Okay, so this character is computed in constant time. Okay, then we update I. So uh, we compute psi prime I modulo n plus 1. Then we obtain psi I. Okay. So the next I is the lexicographic order of the second character of the string. So here we compute psi 3. So we go to this position. Then the next character is C. Okay. So this and this are the same. So next we compute psi, then we go to 0 and obtain the first character. So if we repeat this algorithm, then we can obtain this substring AC tag. And to obtain this substring, we don't need any computation of SAI, and we don't need the T itself. Okay. So then counting query is done in order P log n time by binary search. Okay. So in each step of binary search, we compute a substring of length P. It is done in order P time, and we repeat this log n times. So time. So the time complexity is P log n. This is the same as using the original suffix array and the string T. Okay. But we don't need to use T, and also we don't need to compute SAI, which takes order H time. Okay. And yeah, so T is not necessary. So this psi prime is a self-index because this does not require T to support a query. Okay. And using this idea, we can do partial decoding of a string. Okay. So, for example, we want to decode a substring of T at position 9 to 13, which is here, TDEBE. Okay. So we can use the same algorithm to obtain this substring. So first we compute SA inverse of the first position. Okay. So this is SA inverse is computed by a similar algorithm to compute SA, and it takes order H time. In this case, SA inverse of 9 is 10. So this means that the suffix starting at position 9 has lexicographic order 10. So it corresponds to here, I equals to 10. So now we know I is here. Then the first character, this one, is computed by just dividing psi prime I by n plus 1. Then we obtain this character. Then to obtain, so this is this character, and to obtain the second character, we compute the psi. Then we go to this position. Next, this is psi I, and the next character is t, so we get this t. And to obtain the third one, we again compute psi. Then go to this place and get e, and so on. Okay. So if we can compute the inverse, then we can decode substring of t. So these are the functions of the compressed suffix arrays. So we can compute SAI in order h time, and also SA inverse in order h time. And inside the data structure, we use psi I, and it is computed in constant time. And we can, for pattern search, we need substring, which is of length L, and its position is SAI. This is done in order L time without computing SAI itself. And we can also decode a substring of the text at position J and length L in order H plus L time. And the space is N times 2 plus log sigma plus order N log N divided by H plus order L log N over log N bits. So this is, the space is the same as the original compressed suffix array. Okay? But now we don't need to store T, and the query terminal complexity is improved. Okay? So, and for pattern search, oh sorry, the pattern search algorithm is not improved yet. So now I explain how to improve the time complexity. Okay. So then we use this backward search. To search for a pattern P, we do this algorithm. Okay. So if P is ABA, then so LR is the range of the suffix array corresponding to a pattern. And precisely, we first search the last character. So we first compute, we assume that there is some terminator here. Then first LR is 1 to n, so this is the entire range of the suffix array. Then next we want to compute the range for pattern A, which is here, 1 to 3. Okay. To compute the next, we update LR to 1. This is 0. Next, we want to update the range to 1 to 3. So how to do it? So so we compute this one. So among all j in C of pk, here pk is the last character, so this is a, and ca is 1 to 3. So for all j from 1 to 3, choose the smallest j such that psi j is greater than or equal to L. In this case, L is 1. So here we choose the smallest j such that psi j is greater than or equal to 1. So in this case, L equals to 1. Okay. Then R is the maximum j such that psi j is smaller than or equal to r. So in this case, here r equals to n. So n in this case, r becomes 6 and 3. Okay. So we get this one. Next, we consider AB. B. To given the range of for pattern A, that's pattern A, we want to compute the range for BA. So we prepend one character B to A. Okay. So next we want to compute the range of BA. It is here. BA appears here. So L is 4 and R is 5. We want to compute this. So then we look at CB 4 to 5. So we look at this one. So L is the smallest, L is the smallest j such that psi j is greater than or equal to current L, which is 1. So, so, so here, so L is the smallest j such that psi j is greater than or equal to L, and now L is 1. So, okay, sorry. So L is here, and R is the largest j such that psi j is smaller than or equal to 3. So R is here. So next we get 4 and 5 for pattern BA. So this is pattern A. Then finally we consider pattern ABA. So we prepend A to BA. So CA is 1, 2, 3. So yeah. Among these psi values, we compute the smallest j such that psi j is greater than or equal to 4. So L is here, and for R, find the maximum j such that psi j is greater, so smaller or equal to 5. So R is here, okay? Because 6 is greater than 5. So finally we get 1 and 2. So this is the graphic order of ABA. So we get this one. Okay? So by this algorithm, we can obtain the range for pattern P. Okay? So we repeat this P times, and each step we do a binary search on psi twice. Okay? So each binary search takes order logarithm time because psi is computed in constant time. So the time complexity is pattern length times log n time. Okay. So here we don't compute SA. So there's no age here in the time complexity. Okay. So the time complexity is P log sigma, which is the same as using the original suffix array. Okay. Next, we consider the compressed psi. So the size of psi prime is n times 2 plus log sigma plus little o n bits. Okay. So this is greater than t, the string, because t just uses n log sigma bits. Okay. So psi prime is always greater than t, okay, larger than t. So we want to compress it in less than n log sigma bits. So how to do it? Then let S, the set S of C is the set of indices I, such that T of SAI equals to C. So this means that I is the lexicographic order of a suffix whose first character is C. Okay. So here this is S of Dara, and here this is S of A, and this is S of C, B, and this is S of C. The set is includes lexicographic orders. Okay, and let n sub c is the cardinality of the set. So this is equal to the number of suffixes whose first character is c. Okay, so nc is na is 3, nb is 2, and nc is 1. Okay, and for indices I in set S of c, we represent psi I by a bit vector of length n. So, for example, uh, S of A, the set is sorry, we store psi I, so the set is 4, 5, 6. So we represent this set by a bit vector B A. So 0, 0, 0, 1, 1, 1, 0, 0, 0. Okay, so for sorry, not this, not this. 0, 2, 3, 4, 5, 6. Position 4, 5, and 6 have 1. Okay, because I want to represent this 4, 5, 6. Okay? And for B sub B, the bit vector is 0, 0, 1, 1, 0, 0, 0, because we want to represent this 2 and 3. So positions 2 and 3, there are ones. Okay, and for B, C, the psi is just 0, so we store 1, 0, 0, 0, 0, 0. Okay, so if we store these bit vectors BC, then yeah, it's easy to compute psi I by just select one of B, C, and I. So for BA, sorry, this is not the some we have to so we here this should be I minus some C of C. So where C is the first index of the suffix. First character is C minus 1. So for if the character is A, then this value is 0. And if 0, and if the character is B, then C of B is 3. Okay? So to compute psi 4, we subtract 3 from I, then we compute 4 minus 3, then we find the first in the position of the first one in B sub B, then we get 2. So psi I is computed from the bit vector and the index of the first index for each character. Okay? And the bit vector B sub C is of length n, but because it's a sparse vector, we can compress it by using the data structure GV for compressing a bit vector. We can compress B sub C in NC times 2 plus log of n over NC plus order NC log NC over log NC bits for each character C. Then the total space is the summation of this term. Then this is upper bounded by n times h0 plus 3, where h0 is the order 0 entropy of the string. And h0 is at most log sigma, always. And this equality holds if all the characters appears at the same time. So N1 P1 is the probability that the character 1 appears. So here PC is NC divided by N plus 1. Okay. Yeah, it's easy to prove that H0 is at most log sigma. Okay, so H0 is defined by this is entropy, order 0 entropy, and from the concavity of logarithm, we can obtain this upper bound. Then this is cancelled, so this is log sigma. Sorry, the definition is here. Okay. So if the entropy is small, then n h0 plus 3 is smaller than n log sigma. So if sigma is large enough, then this h0 plus 3 is smaller than log sigma. So yeah, of course this is upper bound. So this is does not hold. Yeah, this this always holds. So in general, in practice, the space is much smaller. So then if the entropy is small, then we can compress psi smaller than L log sigma. Okay. Okay. So here I showed how to compress psi. So psi is represented by sigma bit vectors. Okay. So now we don't store psi prime. Instead we store psi. So then if we have psi prime, we can compute T of SAI. Okay. But now we don't have psi prime. So instead we use a bit vector, another bit vector D, defined as follows. Okay. Di is 1 if and only if I equals to 0, the first one, or T of SAI is different from T of SAI minus 1. Okay. So here D is 1 because the first character A is different from the previous one. And here D is 1 because the first character T of SAI is different from the previous one. Okay. And also here. Then T of SAI is computed by taking rank 1. So the rank is 1, 2, 2, 2, 3, 3, 4. Okay. So rank 2 corresponds to A, rank 1 corresponds to Dara, rank 3 is B, and rank 4 is C. So then it's easy to convert these rank to these characters by just a simple table. Okay. So, and rank 1 is, if we store the bit vector D without compression, then we can compute rank in constant time. Okay. And the length is just n, so we use n bit. So this the first character is computed in constant time, and the space is sigma times log n plus log sigma. Okay. So we use this array C inverse. It is of length sigma, and each entry is just a character, so log sigma bit. And and so sorry, we store D, but because this is also sparse vector, we can compress it. But if we use the data structure GV, then rank is not constant time. So we use another compression algorithm called FID, free indexable dictionary. Then we can compress it into sigma log n bits, and rank is done in constant time. So we don't need to store psi prime, and we can compute t of SAI in constant time. So we obtain this theorem. For a string of length n, its psi function is stored in n times 3 plus h0 plus some small term, and psi I and t of SAI are computed in constant time. So then and we can support pattern search in order p log n time, and we don't need t. Okay. Any question? Okay. Then next, to consider how to compress suffix trees. So, I already explained the suffix tree. So it is a tree structure to store all suffixes of a string. Okay. So the suffix tree consists of the string, which uses n log sigma bits, and the tree structure. So there are at most 2n nodes. Okay. So if we use a naive or standard data structures to represent the tree, then it uses order n log n bits. Okay. And for each internal node, we store string depth. Okay. So there are at most n-1 internal nodes. So the space is n log n bits. Okay. Because the depth is, in the worst case, n. Okay. And we also need to store h labels. But instead of storing the characters like this, we store a pointer to the string. So this BA is here. So we store the pointer to this substring. So for each node, we need one integer. So we use n log n bits. And we also want to store suffix link. Okay. So for each internal node, we have one link. So we also need n log n bits. Okay. So the first component, string, is the input and n log sigma bits. But in addition to this, we use these 4 components, and each of them are at least n log n bits. So the space is much larger than the input size n log sigma. Okay. Yeah, here we consider n is much larger than sigma. Okay. So we want to compress these components. Okay. So yeah, we compress each component. Okay. So first consider the tree structure. Okay. Yeah, it's easy to compress it because we can compress the tree structure by succinct ordered trees. For example, the balanced parentheses sequence. Okay. Then a leaf is represented by this pattern, and there are n leaves, and internal nodes are represented by a pair of open and close, and the number is at most n-1. Okay. So the tree structure is represented in at most 4n plus little o of n bits. Okay. And a node is represented by the position of the corresponding open parenthesis. Okay. This is already explained. Okay. So So given the position V of the open parentheses of a node, we can compute a pre-order and in order of that node. The pre-order is just to count the number of open parentheses. Okay? And from the pre-order to the position, we can just compute select. Okay? And this in order is important for suffix tree, so we need to compute this. Yeah, I already explained this in order, but so let's recall this. So in orders are defined for only internal nodes, and the definition is that the number of internal nodes visited from below during the FS traversal from the root to the node V. So this node has in order 3 because during the DFS traversal, we visit this node and this node before that node. Okay? So during DFS, we go like this and like this. So before coming to V, we visited 2 internal nodes. Okay? So this node has in order 3. And an internal node may have more than one in order. Precisely, a node with degree k has exactly k minus 1 in order. Okay? So a unary node doesn't have an in order. Okay? This is unary. But in suffix trees, there's no unary nodes. So any internal node have at least one in order. Okay. Then we can convert the position V and its smallest in order I in constant time. Okay. I already explained this. But so given the position V, its smallest in order I is computed by this formula. So yeah, if V is here, we go to the next position V plus 1, then compute the find the close, then count the number of leaves. Okay. Then we get 3. And given the smallest in order I, we can find the position in the sequence by this formula. And these are done in constant time. Okay. Then next, how to compress string depth of nodes. Okay. So first, consider this height array. This is an integer array, and this height array stores the length of common prefixes between 2 adjacent leaves. Okay. So, for example, between this leaf and this leaf, the length of the longest common prefix is 0 because this string begin with Dara and this string begin with A, so there is no common prefix, so the height is 0. Next, consider the suffix at position 1 and position 3. They share the common prefix of length 3, A, B, A. So it's so the height array is 3. Okay, and for this suffix position 3 and this suffix position 5, the length of ACP is 1. So we store 1 and so on. Okay, and these numbers, the length of the common prefix, uh, represent the string depth of internal node. Okay. For example, this node is of string depth 3, and this is equal to this value. And this node has string depth 1, and it is represented by this entry. Okay. So if we have this height array, then we can compute string depth of an internal node. So, okay, this is the definition of the height array. Height of I is the length of ACP between two suffixes adjacent in the suffix array. Okay, so yeah, this tree is the length of the common prefix. Okay, okay. Then the size of the height array is also n log n bits. Okay, because height is in the worst case n. Okay, but actually we can compress this height array. But before showing how to compress it, consider how to compute string depth using this array. Okay, the important property is that height I is equal to the string depth of node with in order I. Okay, so to compute the string depth of a node, if we know its in order, then we can obtain the string depth by looking at the height I. Okay, so the in order is computed by this formula. So given the node V, we can compute in order in constant time, and then we look at the height array. Then we obtain the string depth of a node. Okay. Okay. And next, how to represent H labels. Let I be the in order of node V. Okay. Then ith leaf is a descendant of V. Okay. Because this node has in order I, and it corresponds to ith leaf. This in order I is defined during DFS traversal from ith leaf to the next leaf. Okay. So these H labels is a substring of SAI. Okay. So to obtain these labels, we compute this. So first compute the in order. Okay. Then we know the string suffix. Then next we compute the string depth of V and its parent. The string depth of V is just height of I, and we already know I. Okay, so we can compute D2 height of V. Okay, and the string depth of this node parent V is also computed by first, first go to parent, then compute it in order, then look at the height array. Then we can compute D1. Okay. Then h of VD, the D character on that edge is just this character. So this is a substring of SAI, and the position is that D1 plus D plus SAI. Okay. So this character is this one. Okay. And this character is obtained by if we can compute the SAI. Okay. So this is not a constant time if SA is compressed, but we can compute in order log n time. And we can also compute the edge length by just D2 minus D1. Okay. So if we have the height array, then we can compute the edge labels. So now we consider how to compress height array. Okay. Given I and SAI, then height I is computed in constant time using an index of 2n plus little o of n bits. So we can compress the height array from log n bits to just 2n bits. Okay. So how to compress? So to compute height array, we permute the values or rearrange the values. So this is input 0310, and the suffix array values are like this 7135. Then consider the summation of SA I and height I. Okay. Then the values are 744, so 0 plus 7, 3 plus 1, 1 plus 3, and so on. Then 5, 4, 4, 6. Okay. Then we sort this SA plus height in order of the SA values. Okay. So yeah, this one go to the first place, and these two go to the second place. These three go to the third place. Okay. And then this go to the first place. This go to the second place. This go to the third place, and so on. Then this becomes increasing. Okay. So how to prove it? Okay. But yeah, okay. So if there is an increasing sequence, then we can compress it. Okay. So if there are n numbers in between 1 and n, then these numbers are represented in 20 bits by using a unary code. Okay? Unary code of differences. Okay? So the first value 4 is encoded by 0001. 4 zeros and 1, 1. Okay? The next value 4 is the same. So the difference is 0. So you just encode 1. The next one is also difference is 0. So encode 1, 1. And here, this is 1 greater than the previous one. So we encode 0, 1. Okay? So this is also 1 greater, so 0, 1. This is 1 greater, so 0, 1. Then the length of this sequence bit vector is 2n, at most 2n. Yeah, there are n exactly n ones, and the number of zeros is at most the last value, and the last value is at most n, so the length is at most 2n. So how to prove that why we obtain an increasing sequence? Okay. So then consider this lemma. Let SAI be P and SJ. Sorry. Let I and J are indices of suffix arrays such that SAI is P and SAJ is P plus 1. Okay. So in the SA, okay. Then the height J is greater than or equal to height I minus 1. Okay. So how to prove this? Assume that height I is D. Then if we consider okay, so height I equals to D means this suffix and this suffix, this adjacent suffix share the first D characters. Okay, then and assume that these positions of these suffixes are P and Q. Okay? Then if we consider the suffix at position P plus 1, its lexicographic order is J by definition. Okay? And consider this suffix Q, and if the suffix at position Q plus 1 is also adjacent to the suffix at position P plus 1, then the length of HCP is 1 smaller. So this is D minus 1. Okay. So in this case, height J is height I minus 1. Okay. But there are another case. Okay. So if Q plus 1 goes to another place, which is not adjacent to P plus 1, then in this case, the height of J may be greater than D minus 1. In this case, it is, yeah, good. the LCP is 3, so this is greater than 2. So in this case, height is greater than d minus 1. No equality. Okay. So this holds, this lemma holds. Okay. So within this formula, we just replace J with SA inverse of P plus 1 and replace I with SA inverse of P. Okay. Then we use this property to height of SA inverse 1 plus 1 is smaller than or equal to height of SA inverse 2 plus 2, which is smaller than or equal to height of SA inverse P plus P, and so on. And the first value is at least 1, because height is always non-negative, and there is plus 1, so this is the smallest one. And the last value, height of SA inverse n plus n, is because the last one is Dara, so the height is always 0. So the last value is n. Okay. So there are n numbers, and between 1 and n. Okay. Yeah. So this is a monotone increasing sequence in the range 1 to n, and there are n numbers. Okay. So we can compress it into 2n bits. So how to compute height I? So first compute SAI. Okay. So if we store the uncompressed suffix array, this takes constant time, but if we use a compressed suffix array, then the time is log n to some epsilon between 0 and 2. Okay. Then from the bit vector, we decode the kth element by using the select function. So then height I is computed by v minus k. Okay. So height I is computed in order log n time, and the space is 2n. Okay. Okay. Next, I want to compute suffix links, and to compute suffix links, we use LCA. So let's recall this. So LCA is a lowest common ancestor between two nodes. Yeah. LCA between V and W is this node. This is a common ancestor and lowest or nearest. And this is done in constant time, as you know. So consider the excess array. Then HA is computed by range minimum and parent operation. Okay. Yeah, in this case, V is here, and W is here, and compute the range minimum. Then we go to the parent node. Then we obtain the LCA. Okay. So then we can compute suffix link. The definition is that the suffix link of a node whose label is C alpha, where C is a character and alpha is a string, is the node whose label is alpha. So if the its label, not its label, label of this node is C alpha, then its suffix links point to another node W whose label is alpha. Okay. So there may exist some other nodes. Okay. So to compute suffix link, we can use the psi function of the compressed suffix array. So this is the algorithm. So first compute x, which is the leftmost leaf below v. Okay. In the subtree rooted at v, we compute the leftmost leaf and rightmost leaf. Okay. And the leftmost leaf x is computed by this, and rightmost leaf is computed by this. I already explained how to compute the rightmost and leftmost leaves. Then we compute psi x and psi y. So this x goes to this x prime, and this leaf goes to this y prime. Okay. Then W is actually the LCA between x prime and y prime. So this is done in constant time. Psi is computed in constant time, and also LCA is done in constant time, and also select and rank constant time. Okay, and we don't need any extra index except for rank on leaves, rank and select on leaves. So how to prove this? So first, consider what is x and y. As I already explained, leaves are represented by this pattern and appear in the balanced parenthesis sequence P in lexicographic order of suffixes. So the leftmost leaf below V is computed by this, and this is the rightmost leaf. Okay. Then the leaf X represents the suffix whose position is SAX, okay, and Y represents the suffix at SAY. Okay. Then if we compute psi, then X prime represents the suffix at position SAX plus 1, and Y represents the suffix at position SAY plus 1. Okay. Yeah. X is the leftmost leaf and Y is the rightmost leaf. Okay. Then let L be the length of LCP between X and Y. Then this L is identical to the string depth of V. So from the root node, the label is of length L. Okay. Then LCP between x prime and y prime is L minus 1 because we just remove the first characters of the suffixes. Okay. Then, so x prime and y prime somewhere, and the LCP is L minus 1. So this means that from the root node, this label is of length L minus 1. Okay. So this node represents a string of length L minus 1, and so the label of V is maybe C alpha, and label of this node is alpha because x1, x prime and y prime are suffixes of x and y. So the first alpha characters are the same as alpha. Okay? So this node is the node pointed to by the suffix link of V. Okay? So then we can just by computing LCA between x prime and y prime, we can obtain the suffix link. So we also consider suffix tree operations. So how to go to a child node. So we want to compute this child VC. Okay? So this is a child of V, which each label starting with letter C. Okay? So we want to compute W. So there are three algorithms. The first one is we enumerate all children of V. Okay? We can enumerate child by using the first child and sibling operations on the succinct tree. Then for each child, we compute the first character of that edge. Then if it is C, then it is the answer. The node is the answer. Then the second algorithm is that instead of enumerating all children, we do a binary search using the operation to find ith child of V. Okay? We can do this in constant time. So we can do a binary search. Okay, and the last algorithm is a binary search on the suffix array. Okay. So this is this. So V may have many children, and we want to find some node W such that the first label of the H is C. Okay. But to find this, we consider the all descendants of V. Okay. Then So compute the leftmost leaf of V and rightmost leaf R of V. Okay. Then we do uh, a binary search on this suffix array. We implicitly store suffix arrays. Okay. And then the suffixes in this range are of course sorted, and their first characters, their first D characters are the same. Okay. D is the depth of V. Okay. Then we can find some range of suffix array whose D plus D plus first letter is C. So then by a binary search we can find these leftmost and rightmost leaves satisfying the condition. Then by computing the LCA between these leaves, we can find the W. Okay. But in any algorithm, we have to compute H or suffix array entries. So this is not a constant time. We have to compute SA. So it takes at least log n time. So, this is a summary. So the complex suffix tree consists of the following components. Okay. Complex suffix array and the balance sequence of the tree structure, whose space is 4n plus little o n bits. And the height array has 2n plus little o n bits. Okay. And this is the size of the complex suffix array of the string. So H labels are represented by the height array and the CSA, and also suffix links are also represented by psi function of the complex suffix array. So, and any operations can be done on these three components. And the size of the complex suffix tree is the size of the complex suffix array plus 6n plus little o n bits. Okay. So CSA is the space is n times h0 plus 3 at most. So if entropy is small and sigma is a bit large, then this space, the size of the complex suffix tree, may be smaller than the string itself, n log sigma. But there are 9n, so this holds for a large enough alphabet. And the time complexities of operations on the complex suffix trees are as follows. So we can go to the root in constant time, and we can check if a node is a leaf or not in constant time. And we can also find first child, sibling, parent, and node depth, and LCA in constant time. These are done just using the balance sequence of the tree structure. And the string depth of a node and the edge operation, the teeth character of H level is done in order T of SA time, where T sub SA is the time to compute an entry of the suffix array. Okay? So this is not constant time, but roughly order log n time. Okay? Or faster. And the time to compute a suffix link is order T sub psi time, where T sub psi is the time to compute psi array. This is constant. And the child operation takes order T sub SA times log sigma time. Okay? Because we do a binary search, and in each step of the binary search, we compute H, and it takes order T sub SA time. So a child can be found in T sub SA time log sigma time. So T sub SA is in general order log n time. So this is order log n times log sigma time. Okay, so this is a bit slow. So this is a drawback of using compressed suffix tree, but space is greatly reduced. Okay, maybe n log sigma plus maybe 5 n log n bits. This is n log nh0 plus at most 6n bits. This is much smaller than the original suffix tree. Okay, and these are the differences. The compressed suffix arrays is proposed in this paper, and this is about the self-index. Okay, and this is a compressed suffix tree. Okay, any questions? No question? Yeah, then finish. See you next week.